I'm Vinay. Today I'm going to present a case study, you can say, on mechanistic modeling of twin column chromatography. So until it appears, I just want to make a disclaimer also. I'm an employee of Biocon, but definitely I'm going to present this case study from the NCL part because I'm in collaboration with NCL, and this work was done under the guidance of Rahul. So even I am very thankful for Rahul to setting up the stage for topics like continuous chromatography. So thank you, Rahul, for this. And this work is a masterpiece work done in Rahul's lab by Mr. Prashant and the team. So this is how we are correlated in the industrial and academic collaboration. And we will talk once it is appearing. So before we start, let's understand the biosimilar marketplace. So India is a potential market for biosimilars, and we can say, like, in upcoming time, we can see 1.8 billion mark to be touched by the industrial Indian biosimilar industries only. And there are nearly 25 industries in India which are at least targeting one dedicated molecule for international market, and they are having a good pipeline though. And these molecules are especially antibiotics and antibody and antibody fragments. And we can say, like, these are majorly for oncology treatment. So we definitely understand there is an opportunity for growing market of biopharmaceuticals worldwide. However, there are the challenges like capacity enhancement, scale up to meet the demand, and high investment in the same regime. So now for the solutions, as even Rahul explained, we can work on the process intensification to use the best technologies in our facilities. We can opt for continuous processing with the high productivity targets, low investment time during development, and definitely less pumping of money for the development processes. Now, using the modeling, we can definitely predict the process and design the process very efficiently. So this is how we can say. And before we start, let's understand what is batch to continuous, and then we can see how it works. So like in short, if we say, so in batch mode, we load complete product on a single column, and it is designed in a way like breakthrough capacity is not more than 10%. And it is done to save the product going in the loss. So because of this, we underutilize the resin. And because of this, the productivity is also less. Now, if in same regime, if we in continuous process, what happens if we can collect the breakthrough from first column on to the second column, definitely we can increase the unutilized capacity of the resin. So rather than 10% of breakthrough, if we target 70, just select as a number as 70, and we move forward, so the first column will be completely loaded, as you can see in the second figure, and the breakthrough can be collected on the second column. So this is how we can utilize the capacity of both the columns in a way. So just to explain in pictorial diagram, we can say, like, here you can see on the left hand side, there are the two columns which are connected with each other. The first column is loaded, and once it is crossing the maximum loading capacity, the breakthrough from the first column can be collected on the second. So when we move towards the right hand side top figure, we can see, like, the breakthrough from first was captured on the second column, and the first column can be disconnected, and this disconnected column can be further taken for washes, elution, and again regeneration to have a further loading again. So during this time, what happens, the second column, you can see in the later figure, the second column goes through the loading, and the similar way, when it is overloaded, the breakthrough is captured on the first column. So this is a cyclic process, and this is how continuous process for twin column works. So now let's understand the mechanistic modeling of this continuous process. So let's see what is mechanistic modeling. So mechanistic modeling is basically a mathematical approach to predict the performance of the liquid chromatographies underlying the physicochemical processes which are happening in the column. So now, mechanistic modeling, if actually done well, it can predict our processes well, and it can provide a better robustness. Now, mechanistic model also, if calibrated well, and it can help you to even extrapolate the information rather than only interpolation, because most of the model, when we see, it is within the range what we give and they provide the information. But if it is done well, we can even extrapolate the information at different operating conditions also. So, and the last thing I will say, like in upcoming days, we have seen like the PAT initiative, which is Process Analytical Tools. It has been fueled well, and there is a lot of interest to understand like bioprocess unit operations and how they work. So this initiative is helping the mechanistic modeling to come up for the evaluation for most of the bioprocess unit operations. So now in this flow, let's understand when we talk about continuous capture process. So firstly, we need, initially some experiments are required, like we can say like breakthrough curves of 3 different RTs or feed concentrations. Along with that, we definitely need some information about the resins, like column length, what we are going to use, bead particles, particle porosity, then linear velocity and adsorption parameters. Along with that, mass transfer parameters are also required, which can be derived from the breakthrough curves which were generated. And we are going to talk about these in upcoming slides. So when we have all these parameters, we can again model it and predict the extrapolation ranges what we are targeting. And we can also look at the productivity and capacity utilization of the continuous processes. So once we predict, definitely we have to go for validation, whether the productivity what we have measured or the breakthrough we are predicting is well or not. So this can be validated through the experimental numbers, and we can verify the same. So now before we move, so I think we have seen the similar figure in Rahul's presentation. So the mass transport processes which is working nearby the bead is film diffusion, absorption, pore diffusion, axial dispersion, and surface diffusion. And this is well explained by the general rate model. So mass transport, what happens in the column is because of the solute moving through the interstitial column volumes with the connective flow. And there are the broadbanding issues which are explained well by axial dispersion and like resistance because of the film diffusion and pore diffusion, as well as the surface diffusion and the absorption inside the bead particles. So now let's talk about the mathematical framework in this general rate model. So mathematically, we have to work around the bulk phase mass balance equation, which is the first one. Second is the particle phase mass balance equation, which tells about the total amount of product within the bead. And absorption is well explained by the Langmuir adsorption equation, which is the equation 3. So all these 3 equations, when fitted and solved with the help of CAD framework, which is chromatography analysis and design tool, we can drive the mass transfer parameters. So now for model framework, if we look at, for the continuous process, we have to understand this graph. So what happens, like as you can see the line going up, this is a breakthrough curve, and the point where it starts is the 1% of the breakthrough. So in continuous process, what happens, anything which is coming into the breakthrough need to be captured on the second column. So the area under the curve is an area which has been captured on the second column, and area above the curve, what we are targeting and denoted as S, is the amount of product which will be on the first column. So this is very important. And for this, we need to know the time, how much time it will take to achieve the breakthrough, what is denoted as S. And definitely the flow rate is important because these 2 parameters are going to help to calculate the productivity and capacity utilization. So as you can see, like productivity, as we coin the term and we say like the total protein purified per unit of time and resin volume. And we consider 100% of yield because there is no intention to lose the product. And capacity utilization is the second term. What we have to consider for the continuous process is like what amount of protein is being binded and what is the capacity on the resin. So these are the 2 important factors we have to consider in the model framework. So now here onwards, we can see like what is being done. So as we described earlier, so the breakthrough curve at 1, 5, and 10 mg per ml feed concentrations were plotted and at 2 minute residence time. And from these breakthrough curves, we have derived the mass transport parameters like dP, ds, kf, and dAx, which is pore diffusion, surface diffusion, film transfer, as well as axial dispersion. So these parameters were derived, and then we have correlated with the actual experimental data, and we have seen like both are matching well. So you can see the line graph is experimental data, and the simulated data is coded with the blue color. So now the parameters derived from these predictions as well as the mass transport parameters were used further to predict the breakthrough curve at 15 mg per ml. And you can see like at a 2-minute residence time, and the same was validated with the actual experimental data. So the curve was actually fitting well, and you can say with the 5% of error, we were predicting really well with 15 mg per ml. So this information was further used to check the performance for the continuous process, especially for the productivity. And we have seen as we increase the feed concentration, like in the first graph on the left-hand side, 5, 10, and 15, the productivity increases. However, the capacity utilization is not much impacted as we increase. So this is a thing, and so we have experimentally predicted as well as whatever experimental data and the predicted data was matched, and you can say with the 2% and 3% of error, it was matching well. So now we have a model now which is working somehow. So we have extrapolated the information for bigger ranges. So the feed concentration of 15 was further increased to 20 and 25. And at different residence time of 2, 4, and 6 minutes, and the graph obtained from the prediction was actually matching with the expectations, and this was further compared for productivity as well as capacity utilization. Sorry. So here we can see like as we increase the feed concentration, the productivity is increasing, although the capacity utilization is not impacted because the target of loading was not changed. But because we increase the feed concentration, so total volume goes low, and we can see the productivity and total binding can have a better, within the less time we can process the product. So that is how we have seen the impact. However, with respect to residence time, when we increase the residence time, the total time to achieve the complete loading will be higher, so the productivity is going down. So this was betterly correlated, but we have understood the breakthrough percent also plays a major role. So in upcoming slide, we can see like at lower residence time, when we have compared the different breakthrough target percentages like 60, 80, and we can see the highest productivity is seen with the highest target breakthrough at lower residence time. But when we compare with the, lower residence time, but with the higher residence time, there is no impact. So there is an interaction between the target loading capacity and productivity. Okay, so now when we talk about the residence time, there is no impact, as well as we can see like with a higher residence time, there is no impact on the capacity utilization. So based on this information, we have understood like feed concentration, breakthrough percentage, and residence time are the major variables, and they may have impact on the productivity. So based on the model, the complete DOE was formed, where we have kept a feed concentration from 5, 10, 15, and 25 mg per ml, breakthrough percentage of 60, 70, and 80%, and at a residence time of 2, 4, and 6. And the productivity was predicted, and when it was fitted in the model, we can see like we have found the significant impact of feed concentration on productivity. So as we increase the feed concentration, productivity goes up. Also, with respect to the residence time, if we see, as we increase the residence time, productivity goes down. So these are the two major factors, but when we compare the breakthrough percentage, there is no major impact, and it is non-significant also. And model was fitting well with 0.93 R-square value. So based on this complete information, if we talk, so we have understood like a feed concentration, residence time, and breakthrough has some interactive impact, and it is complicated to actually design the process in the traditional way for the continuous process. But if we use a model-based approach and a target-oriented design. So with the help of modeling, we can do it very easily. Now, the three major steps as we have discussed. So the initial one is to have at least breakthrough curve at various feed concentrations, fitting the things to get the mass transfer parameters like dPds, Kf, and dx. And these can be further used for prediction at different feed concentration and residence time. And we can calculate the productivity and capacity utilization with the same model. And we can even work with the feasible window of feed concentration as we have seen, like which is the best one for the optimization, and we can select, and we can validate with the experimental data. So this is an overall view of the presentation. So now, if you see, like this is an overall summary from the last slide. So we can at least reduce the 50% of overall process development time and cost with the help of modeling approach. So mechanistic model, I will say, definitely is helping us on this front. And you can say like how much experiment we have done versus how much we have predicted and simulated. So the concluding statements are here, like mechanistic model based approach for development was used for twin column setup, and it is working fine. And the various parameters like breakthrough curves was predicted. And we have also understood the impact of productivity and capacity utilization based on prediction. Based on this, we have identified like feed concentration, residence time, and breakthrough loading is definitely going to impact the continuous process. And based on the modeling, we can select the operating window which is feasible, and that can be validated based on the experimental data. And I will say definitely it is a feasible and reliable approach for continuous process development with respect to mechanistic model. Yeah. So I just want to thank especially to Mr. Prashant and Dr. Rahul Bambure for this work. This work was definitely done in NCL, and it is under the industrial collaborations. So thank you so much from my end.
I think this is very interesting topic, but a tough topic for all. There is no question, or it's a very easy topic.
So after lunch, in fact, it's not
yes.
there.
It's okay. Yeah, please.
Hi, my name is Girish. I'm from Reliance. Yeah. So just would like to know, like, what was your aim when you started this work with Rahul's lab?
Yeah.
So what you had in mind, why you wanted to get this work done? Okay.
So as you know, like we are having different processes in our commercial manufacturing. So the target was to implement the new generation technologies, which is one of the things coming up as a continuous process. So Affinity was the target, and that is how we have decided to do something on this continuous chromatography front for capture. And modeling came up because of one reason, because initially nobody wants to spend more time on failing several times, deciding something, then learning from the failures. Can we have a model-assisted feedback? So Dr. Rahul was working on this. I will say there was a proper guidance from him, and we have thought like definitely let's do it, and it can be used.
Thank you.
It's not a question. I would say I'm curious to know. This your mechanistic model is applicable to all chromatographic modalities, right?
I will say it is only for continuous capture, affinity process. And especially, I will say the resin used is from the Cytiva Prisme resin for your reference, I can say.
Okay. But not with the other modalities.
See, because as I told, like the parameters for the porosity and other relative factors for the resin you consider should be taken in account for modeling. So whatever the resin you can select, you can fit the same thing. But parameters will change. Means the numbers will change.
Right. Yeah. Got it. Thank you. Yeah.
So one more, last one.
So I just wanted to know what is the highest scale at which you have tested the model?
So I will say this is a, just for information, I'm telling this is a scaled down model, what we typically use in industry at lab scale, and to be very precise, it is a VL11 column, you can say.
Okay.
Yeah.
Why I wanted to know is that so this is for a affinity step, but the similar kind of model can be also developed for a CX step.
Definitely.
Right. And in case of a linear gradient, there will be differences in scale. So
Yes.
whatever linear gradient you would have in your lab scale, it may or may not be exactly replicated when you scale it up. So how does the model, or can you develop a model which takes into account the differences in scale so that you can predict what is going to happen at the
So I will say when we do scale up, it is a linear scale up. So if you are talking about a linear scale up, definitely it can be done. But if you go for non-linear scale up, definitely a few things need to be taken in account for that. Yeah.
The thing is because some variations are due to the equipment hold-ups or equipment.
Yeah, you are right. So can I just suggest you one thing, like what happens in commercial manufacturing and especially in linear gradient, we collect a peak. So peak start within the gradient, and we have a collection parameter based on UV. So I will say that is more important rather than the dilution factor. So yeah, definitely there will be a elution factor difference of, you can say, 0.1, 10% maximum. I don't feel above that anybody consider it. So definitely it is not a big problem as such.
So
Yeah.
we will discuss more about this in the panel discussion, and we will take this point
Yeah.
of this,
Okay.
that how this modeling can be support for the scale ups and all these things.
Okay, thank you so much.
Thank you.